You've definitely seen this before, right? That massive flame lighting up the night sky near some industrial plant. But what is it really? Is it just waste? Something they're burning off to get rid of? Well, the real story is so much more complex, and honestly, way more interesting than that. Okay, let's get into it.
First things first, we got to think about this differently. That pillar of fire isn't about waste. Its number one job is safety. Think of it less like a car's exhaust pipe and more like a highly sophisticated, absolutely critical pressure release valve for the entire operation. It's there to prevent something from going very, very wrong.
So today, we're going to walk through the whole life of one of these things, what we're calling the rules of fire. We're going to look at everything from the initial engineering blueprints to the super strict operating procedures and, of course, the absolute red lines that you can never, ever cross.
So let's start at the very beginning, the design phase. A flare isn't just some pipe they stick in the ground. No way. It is meticulously planned and engineered down to the smallest detail, long before anyone even thinks about lighting a match.
You know, every single piece of this, the width of the pipes, the steel they're made from, all of it is the result of some really complex math. The whole goal is to safely handle just immense amounts of flammable gas under pressure. You can't eyeball that. You have to get it exactly right.
And here's a look at what goes into those calculations. For the sizing, engineers are using specialized software, here it's called Architect, to figure out exactly how big the pipes need to be to handle the flow. Location is a huge deal too. Offshore, you'll see these long burner booms that keep the flame a safe distance away. On land, they can use flare pits. And even the materials get scrutinized. On those offshore booms, for example, weight is a massive issue, so they'll actually use a lighter grade of piping to manage it.
Okay, so the system is designed, it's built. Now what? How do you actually operate this thing safely? That brings us to our next section, the very strict official playbook for ignition.
And this is where things get deadly serious. The rules are crystal clear. You must use a reliable remote ignition system. No exceptions. The source material is explicit. Personnel are strictly forbidden from using makeshift ignition lances. I mean, can you even imagine trying to light something of this scale by hand? It's a non-negotiable rule for a very, very good reason.
And it's not just how you light it, but when. There's a very specific order of operations here. Best practice says you light the gas flare first, before you start up other equipment like the oil burner. And why is that? Well, it's actually pretty clever. That big, stable flame from the flare acts as a giant pilot light, helping ignite the oil burner reliably, which is incredibly useful, especially when it's windy out.
Speaking of the wind, it's a constant factor. Operators are always managing it. You have to set up your work so that the flare is downwind from you, pushing all that intense heat and any fumes away from the crew. And if the wind shifts, the whole operation might have to stop, so you can switch over to a boom on the other side of the platform. It's like this constant dance with the elements.
We've covered the design, we've covered the operation, but now we're getting to the most critical part of all, the red lines. These are the absolute, non-negotiable safety restrictions that you must never, ever cross.
And right at the heart of these red lines are the rules about what can, and more importantly, what cannot be connected to the flare system. It might sound like a minor detail, but getting this one thing wrong can have truly catastrophic consequences. This slide lays it out perfectly. On the left, atmospheric tanks. You must never connect one to a flare. There are two huge reasons why. First, back pressure from the flare system could literally rupture the tank. But the second reason is even scarier. It pulls oxygen into your pipes, creating an explosive mix. Now, on the right, you see that pressurized tanks can be connected, but only if they have a mandatory flame arrestor.
Let's just focus on that for a second. An atmospheric tank has air in it, which means it has oxygen in it. By hooking that up to a flare line full of flammable gas, you're basically pumping an oxidizer right into your fuel line. You're creating the perfect recipe for a massive explosion inside the system itself. This is probably the single biggest danger these rules are designed to prevent.
So what about those pressurized tanks? Well, they're allowed, but only with that critical piece of hardware we mentioned, a flame arrestor. So what is it? Think of it like a firewall. It's a special device inside the pipe that will let the gas flow through, but it's designed to stop a flame dead in its tracks, preventing it from traveling back down the pipe and into the tank.
And just when you thought the stakes couldn't get any higher, you introduce something like hydrogen sulfide, or H2S. This stuff isn't just flammable, it's also highly toxic. So naturally, the safety protocols have to get even more strict. You can't just let this stuff out. It has to be routed safely to the flare to be burned off. And this is where a very specific number becomes a life or death rule. For certain operations involving H2S, if the wind speed drops below 15 knots, that's about 17 miles an hour, everything might have to stop. Why? Because you're relying on that wind to safely scatter the toxic byproducts from burning the H2S. Without that constant 15-knot wind, a dangerous, invisible cloud could settle over the site. It's a massive risk.
So, after all of this, the blueprints, the playbook, the red lines, what's the big picture here? What's the final takeaway from all these rules?
Well, it's this. A gas flare isn't just a fire. It's the final, visible part of a massively complex safety system, and every single rule we've talked about is a lesson. A lesson learned over decades of experience, often the hard way, and written down specifically to prevent a disaster from ever happening again.
When you think about it, all these rules and designs come together to form this invisible shield, a barrier that stands between a totally normal day at work and an absolute catastrophe. And that kind of makes you wonder, doesn't it? What other invisible safety systems, born from these same kinds of hard-won lessons, are out there protecting us every single day without us even realizing it?